Good morning, everyone. Guy here. Thanks for joining me. Today, we're going to be talking about member connections. How do we make sure that the members that need to be connected in our FE model are actually connected? I'll discuss three different models. One that is properly connected, and two that displays some of the anomalies that you will sometimes find in your models. All right, so let's get on the PC and see how we can check whether our model is properly connected. Hello again, everyone. As I said in my introduction, we're going to be looking at three models. The first model is the correct model, and this is the one that's shown on the screen right now. The first thing you want to check that you've got no floating parts in this model, that everything is connected in a single body. How do you do this? First, you make sure that you define a modal solution. This is what I have here, a modal solution that is unsupported. So as you can see below, I have no boundary conditions applied in my model for this solution. What kind of result will I get? What I want 6 modes, as you see here. The first 6 modes have a very low frequency. It's actually a frequency that's very close to 0. 4 are exactly 0, 2 are a bit higher. But what really matters is that the highest of these 6 frequencies, which happens to be 1.461 10 to the minus 4 hertz, is very, very small compared to the seventh mode, which is at 21.7. So you want a big gap between, you want the ratio of your largest rigid body mode to the first flexible mode to be very small. So when you only have 6 rigid body modes like this, modes 1 through 6, then you know that there is a single body in your model. So if I animate this video, you can see that the entire model is moving as a single body. In a minute, I'll show you a model with 2 anomalies where we've got 3 sets of rigid body modes. And as a result, we can conclude that we've got 3 bodies in our model. The next thing I want to do in this model that has no anomaly is to look at the 7th mode. And now the goal is to make sure that everything is connected, that every member is connected. I'll show you another model in a minute where a few members are disconnected at one end. So how do you verify for that condition of a single member or a few members being disconnected only at one end? At that point, you're not going to get a floating member with its own rigid body modes being close to 0. So how do you verify for this? You can look at your mesh. So I'll just display the mesh here for a second. And your software should include a way to display the node numbers. That's what I'm going to select here. I'm going to ask the software to display the node numbers. And by zooming in, you can see here that all the nodes that we see, there's a single node at every connection, which means that the element from the main members, this element and this element, are properly connected to the 2 diagonals that come in and connect at that point. For large models, it might not be practical to look at every section and look at and make sure that every node, that there's only one node at each intersection. Another check that you can do is animate a flexible mode, so a mode such as this one, a mode that has a frequency above 0, and zoom in and make sure that you don't see anything strange in terms of deformation, a discontinuity in your deformation patterns. And this model is correct. So we do not see any discontinuity, but we'll look at another model in a minute where we'll see these discontinuities. In this case, we can see that everything is moving together. Every member seems to be properly connected where it needs to be. Hello again. In my previous video, I said that we would be looking at a model that presents an anomaly. The first model I said we would be looking at is one that has floating members. So I have modified the model of the truss beam and added two errors, which means that we've got two floating bodies, two diagonals that are floating, not connected to the main members, on top of all the other members. How can we say this? How can we see this? We can see it here. For every disconnected body in this model, we get 6 rigid body modes. So here, how many rigid body modes do we have here? We're now up to 18. The first flexible mode is mode number 17. And as soon as I display it, you can see where my disconnected members are. There's one right here, and there's another one right here. So this is a mistake. This is exactly what I meant by our model should have only one body. It should display only 6 rigid body modes. This model has 2 disconnected bodies, so it's a total of 3 bodies in our model, the main one, and 2 anomalies. And that's why we get 18 rigid body modes before we get to mode 19, which is the first flexible mode. So this concludes the presentation for this first model, which present 2 anomalies, 2 bodies that are not connected at all to the rest of the structure. In our next video, we're going to look at another model that has some anomalies. This time, I have reconnected these members only at one end. So we'll see what happens when members are connected only at one end. Hello again. Time now to look at the model that has an anomaly. This is a second model that has anomalies. In this case, I did, as I did before, a non-supported model solution. So there is no boundary conditions here. But contrary to the previous model, this time I only have 6 rigid body modes, 6 frequencies that are very, very low compared to my first natural frequency, which corresponds to an elastic mode, mode number 7. Now, is there something wrong with this model? Well, right away, you might see that this member is behaving a bit strangely. So let's see. How can we detect this? Well, there are multiple ways. In this case, if we animate our mode number 7, we're lucky. We're going to see right away that this diagonal member here is disconnected at the bottom, as you can see. So it's moving freely. So right away, mode number 7 allows us to detect that we have a problem here that needs to be fixed. We need to reconnect that member at the bottom connection. What else can we do to detect such a condition? What I really like to do is to apply a 1G static loading in each direction. So here is 1G applied in X, and then I looked at the displacement in that direction. That's this result right here. And as you can expect, if you apply 1G in the X direction with the beam being simply supported at each end, notice now that I do have the boundary conditions. Of course, you cannot do a static analysis unless you've got some boundary conditions. You can easily see that right away, this solution allows you to detect that this member is disconnected. X is really the best direction here. It depends on the problem. So that's why I always do a 1G in X, a 1G in Y. In this case, Y doesn't speak as clearly. You can tell that there's a discontinuity here. This is dark yellow. The diagonal is dark yellow at the bottom, whereas the back diagonals are yellow, clearer yellow. So there is a discontinuity at this joint. So it means that these members are not properly connected. So this is for Y. This is for 1G in the Z direction. So transverse direction. Again, you can see it. And if you animate that deformation pattern, it helps to see it. But really, it's the 1G in X direction that speaks volume in terms of this member being disconnected. You can also, as a final way to detect this, is ask your software to show the node numbers. And once you've detected that there is a problem, that it's easier to find, of course, but you can tell here that you've got two nodes that are almost coincident, but not quite. So you need to come in and either merge these nodes or go back to your geometry and make sure that you fix this problem. All right, so this is the end of this presentation on the second model that presents anomaly. Hello again. In summary, we've looked at three models. The first model was the correct one. It had all its members properly connected, and we didn't see any discontinuity in displacements at the different connection points. That's what we wanted to model, and that's what our model represented. Then we looked at a first model that had an anomaly. The anomaly was that two members were completely disconnected. This resulted in 3 series of 6 rigid body modes when we did a modal analysis without any boundary condition. Hello again. In summary, we've looked at 3 models. The first model was the correct one. It had all its members properly connected, and we didn't see any discontinuity in displacements at the different connection points. That's what we wanted to model, and that's what our model represented. Then we looked at a first model that had an anomaly. The anomaly was that two members were completely disconnected. This resulted in 3 series of 6 rigid body modes when we did a modal analysis without any boundary condition. To fix this, you need to reconnect these members where they need to be connected. Then we looked at a second model that had an anomaly. This time, all the members were connected, so the unsupported modal analysis gave us only 6 rigid body modes. That's what we want. That's what we should expect from a model that's correct. But when we looked at the vibration modes, the first flexible vibration mode, and especially when we looked at a static 1G loading in the axial direction, we realized that one member was not connected at one of its ends. So we could see it move. We could see that there were discontinuity in the displacements at the connection point. And that's not what we were expecting. That's not what we were supposed to model. In such a situation, if we had continued with that model, this member that was only connected at one end would not have carried its fair share of the load. We would have seen spurious vibration modes for this member, and as a result, we would not have been studied the proper structure. So hopefully this series of videos has convinced you, of the importance of looking at the deformation patterns, looking at the number of rigid body modes that you get when you do a non-supported modal analysis, and make sure that you understand the results, that the results are what you expect them to be in terms of number of free bodies in your model and in terms of members connecting properly to one another. Thanks, and I'll see you next time.